blockchain course, where I talk about the history, categorization, and use cases for the blockchain industry.
I'm awake, man. I'm about to leave. Alright, bye, my phone.
I am Donald McIntyre, founder of
Didn't get
Etherplan.
enough.
What's that noise? I think it's better if everybody mutes their microphones.
No, it's okay.
Okay, I'm the founder of Etherplan. I'm an Ethereum Classic volunteer and director of business development at BIWares, a data science firm. The course is divided in two parts. First is the history, which is today, and it's usually 2 hours. And I talk about the cypherpunks, the first attempts and projects of the cypherpunks to create money on the internet. And then Satoshi Nakamoto and Bitcoin. And then came Vitalik Buterin and Ethereum. Then I explained the consensus mechanisms and Ethereum Classic and Ethereum, no, the split and the philosophy of code is law. So that's today. The next part of the course is part 2. It's categorization and use cases, which is going to be on Wednesday at the same time. So this is the first part of the course. It's mainly for people who have heard, they're just starting in crypto, heard about Bitcoin and Ethereum and NFTs and all these things, but they don't know exactly what this is. That's the main, most audience for this course. But it may have also information for more advanced users who know more about the blockchain and the different types of blockchains, etc. It may have information that is useful as well. So let's start with the history. Everything started at the end of the 70s. There was a technology invented at the time in cryptology, in the science of cryptology, which was called public key cryptography. And basically, before cryptography, for thousands of years, you would encrypt a message and send it to the other side, to the other party where you needed to send the message, and it didn't matter if anybody could intercept the message because it was encrypted. The problem was that both the sender and the receiver needed to know the same exact secret key or private key to be able to decrypt the message. The invention at the end of the 1970s was that with a mathematical function, each side could have their own secret keys that nobody would know, and the sender would encrypt the message with the public key of the receiver, and then the receiver would get the message, the encrypted message, and be able to decrypt it with their secret key, their private key. So that was a revolutionary invention because the internet was already being born. The computers in general were going to the homes, etc., in the early 80s. And the fact that people could encrypt information without sharing the private key was a key invention. So the cypherpunks were born in the 80s, and they saw this technology as a revolution and that it would bring all the benefits of the internet and freedom and liberties and all those things. But they also knew and had the vision that governments and corporations were going to capture these technologies and the internet and do what they're doing today, no? Surveillance, control of population, censorship, and all those things. So the cypherpunks said, okay, this technology can create a lot of freedom for people to interact freely between themselves on a peer-to-peer basis, but at the same time, it could be a threat of the government and things like that. So let's start building tools where we can be protected using cryptography from these threats. So they had 4 main goals. The first goal was privacy, to be able to interact on a peer-to-peer basis without intervention. The other one is that they realized that if they wanted to do commerce, this was in the second half of the 80s, if they wanted to do commerce without depending on government money, which is a trusted third party, they were going to have to create some sort of money for this world that they were creating inside the internet. So hard money was another of the goals. And then in the early 90s came the idea of smart contracts. It's basically, again, to minimize the need of third parties to create these programs that would live on the internet, and they would be autonomous and they would perform certain services and functions. Now, the typical idea at the time was if somebody sold if party A sold something to party B, party B would send the money to a smart contract that would act like an escrow, and when the whatever was sold is delivered, the product was delivered, it could be digital or physical, then the smart contract would see this and release the money to the seller, and it would be an autonomous entity, not a third party, just a program on the internet. And all these three goals had an overarching goal, which was trust minimization of third parties. That was the key of the objectives of the cypherpunks. So later in the 90s, they were working on many things. Cypherpunks were hundreds of cryptologists and scientists and computer scientists, and sometimes they were lawyers and philosophers, and stuff like that. But by the end of the 90s, they started to build some things that are actually key components of Bitcoin today. Bitcoin and Ethereum Classic. The first one was HashCash in 1997. It was invented by Adam Back. Adam Back was basically, what he wanted to prevent was spam. In this world, in this peer-to-peer world, anybody could send 1 million emails and spam everybody, So he said, no, let's do something to prevent spam, because when we use a third party like Gmail, they prevent the spam. But when we are in a free world, a peer-to-peer world, we have to prevent it somehow. So he said, okay, let's do this. Whenever anyone wants to send an email, when a server wants to send an email to another server, let's have the local server of the sender to do a lot of work, computational work, before sending the email. So let's call it a proof of work. So the local machine would get the email, would do a cryptographic hash, which is like a stamp. It's a cryptographic stamp. But to create that stamp, it had to work a lot, say 1 minute of computational work. And then once it creates the stamp, it puts the stamp together with the email and sends it to the receiving server. The receiving server, although the stamp took a lot of work to make, the receiving server, it was trivial for the receiving server to verify that the work was done, the stamp, the cryptographic stamp. So when he got the email and verified that the work was done, then it would accept the email and open it. So this prevented, the idea of this was that it would prevent spam, because if somebody wanted to send 1 million emails, the local computer, the server, would have to work 1 million minutes to send that spam. So that was HashCash, and it was to prevent that's the core proof of work that works today in Bitcoin, and it was to prevent spam origin. Then in early 1998, Nick Szabo, who was another cypherpunk, said, okay, wait a minute, this is an analogy of gold, because in the real world, to create 1 ounce of gold, you need a lot of miners in the world to extract this gold from nature, and it's very costly. And if you think about it, a cryptographic stamp that is created by proof of work, making computers work, is analogous to 1 ounce of gold. So 1 ounce of gold, you could think of it as a proof of work that many miners were working on extract that ounce of gold. And a cryptographic hash or a cryptographic stamp of proof of work is the same thing. It's proof that machines worked a lot to create that stamp. So he connected gold to what he called bit gold or digital gold, doing that analogy. That's a key analogy that everybody needs to understand. a cryptographic hash that is done with proof of work is analogous to an ounce of gold in the real world. And that's the connection between the physical world and the digital world. And that's why we call Bitcoin and Ethereum Classic digital gold. So HashCash and then BitGold. BitGold is also a key component of Bitcoin today. Then in later, in late 1998, Wei Dai, he was talking to Adam Back and Nick Szabo about all these ideas. He had the idea of creating a network. So he said, okay, let's do this. We have BitGold now, so let's get a lot of machines who are all peers in a network, and let's have a subset of these machines do a lot of work using proof of work and create these cryptographic stamps, which we call today hashes, using proof of work. And when one computer creates a cryptographic stamp and they spend, say, $100 creating that cryptographic stamp because they use the computer, it works a lot, and they burn a lot of electricity, so they incur in a cost. They just put that stamp and send it to the rest of the peer-to-peer network, where the rest of the nodes, they just receive it and verify it. Once they verify that the work was done and the machine that sent it spent, say, $100, then let's put in the account of that machine 100 units of a fictitious currency. So that's how Bitcoin works today. You have a large amount of nodes around the world, like 80,000 computers working on Bitcoin. A subset are the ones that work and create the blocks using proof of work, and they send it to the rest of the network, and the rest of the network verifies that. And once it's verified, they credit Bitcoin into the account of the miner. So HashCash, BitGold, and B-Money are the key components of Bitcoin and Ethereum 1 and Ethereum Classic. That's how these are the technologies. Then Hal Finney, in 2004, he had the idea of creating RPOW, which is reusable proofs of work. He said, let's use a different model. Let's use email. So a computer creates a proof of work, puts it in an email, and sends it to another person as a payment in an email. The receiver would receive the email and verify the proof of work with a centralized server that we put there just to help people verify the proof of work. When it didn't work because it needed a trusted third party, not because whoever ran the centralized server, the verifying server, would be the trusted third party. All these technologies, BitGold, B-Money, RPOW, they always had some problem. They didn't know how to create consensus. They didn't know how to stop 51%. In those times, it was 33% attacks because the maximum security that Byzantine fault tolerant had at the time was only 33%. So it never took off. The important thing about private key cryptography that started all this was that each person had their own secret key, and this was never shared with anyone. And the secret key, you pass it through a mathematical function, and it creates a public key. So everybody sends you messages, or in the case of Bitcoin, they send you Bitcoin or ETC to your public key. So this is the relationship between the secret key or the private key and the public key. It is very easy for the mathematical function to create the public key. Whoever knows the public key, which are public in the blockchains, it is extremely difficult to guess or to try to figure out the secret key. And that's the key of public key cryptography. And this is very important for how the blockchain world works. Are there any questions? It's very important for anybody to ask questions whenever they want, because the questions and the answers have a lot of information that clarifies a lot of this. Does anybody have any questions?
Yeah, I actually have a question.
Mm-hmm.
So I noticed when you said you send emails, then you have to do the proof of work, and then it gets it verified. Is that how double spending got solved? So I know when you send something and it has to get hashed and you need proof of work, so you need computational work. and that work is done. Then once it's done, it's able to be verified. And is that how a double spend was solved?
Verification is one of the ways where the fact that all the network verifies transactions and blocks by verifying the hash or the cryptographic stamp of blocks is one way that you reduce double spends. But the real way that double spends were the protection, the tolerance, the fault tolerance against double spends was increased was with a consensus mechanism. I'm going to explain this later. The fact that the hash itself is the sufficient information for all the network to know that that is the correct hash or the correct block. So it's more of a consensus thing that solved it, not really the cryptography itself.
Okay.
The before networks, before consensus was reached with proof of work that has a 51% tolerance, the tolerance was only 33% because the normal computer networks didn't use proof of work; they just used cryptographic means, and with 1/3 of the computers being attackers, you could compromise the network, and that's where you could do double spends, specifically in money networks, no? And
Right.
these networks didn't work. The bridge that I'm going to explain now was realizing that the proof of work is not only a way to create gold, bit gold or digital gold, but also the information that everybody needs to raise the tolerance to 51%. I'm going to explain that in a minute. Any other
Okay.
questions about the cypherpunks and the history? Okay, I'm going to talk about now Satoshi Nakamoto and Bitcoin. So these guys were working all the time on these technologies. All cypherpunks. So Satoshi Nakamoto, one thing that is important is that the fact that Satoshi Nakamoto used a pseudonym um, it was very normal in the community of cypherpunks. Since the 80s, since the late 70s and the 80s, the US government was pressuring cypherpunks and all the cryptologists that were inventing these technologies to actually not make them. And they didn't want, and whenever they invented something, they just wanted them to share it only with the government, because the government considered all this, the Pentagon, the CIA, and all that, they considered this a national security national security issues. So they should be kept as secrets. But the cypherpunks actually wanted to liberate people from the government, so they actually published all these things anyway, and they sent them by email, and they sent them to Europe and other places. And the government prohibited them to talk, to travel, persecuted them. There were trials. They took them to trial. They took them to Congress. The famous case where the guy had to go, a cypherpunk had to go to, one of these cryptologists had to go to Congress and explain everything that he was doing. The guy who invented pretty good privacy. It is a technology that everybody uses now. So that's why many of the cypherpunks used pseudonyms. So it's perfectly normal that Satoshi Nakamoto used a pseudonym because he invented a key technology, and it was perfectly normal. And we can see it today, how governments were going to attack this new technology. In 2008, I think in October, he published the Bitcoin white paper, and the description is very simple. Bitcoin is only a ledger with accounts and balances, and that's it. That's the only thing that it does. You can send new transactions to move Bitcoin from account A to account B, and that's it. So it's accounts, balances, and it accepts transactions. It's extremely simple. The other key of Bitcoin is that any new information that goes into the network, any new transaction or any new block, it has to be fully transmitted. When whoever received the transaction retransmits it to another 20 or 25 nodes in the network, and like that successively, and until in milliseconds or seconds, the whole network has everything fully replicated everywhere. So whenever we send one transaction to Bitcoin or Ethereum Classic or Ethereum 1.0, it gets transmitted in seconds to all the nodes of the network. And because the information is fully transmitted, then they all store it in the database, which is called the blockchain, and it becomes fully replicated. So the key, one of the two great security points of Bitcoin was full replication of the database, that it has to be replicated everywhere. And this is done with full transmission. The full replication is very important because the more nodes have a copy of the full history,
Some professional shit.
the more secure it is. If a network is fragmented, then part of the network could be out, so that the rest of the network doesn't know that information, etc. The most secure model is to have full replication in 100% of the nodes. The way the blockchain integrates new information or new transactions into the blockchain is through blocks. So in the case of Bitcoin, every 10 minutes, everybody accumulates up to 4,000 transactions. That's the limit, more or less the limit of the Bitcoin block size. And when they get the 4,000 transactions, then they do the proof of work and create the cryptographic stamp for that specific block of transactions. And whenever a miner creates a stamp, finds the correct stamp, which is a competition between miners, they immediately send it back to the network for verification. And the rest of the network distributes and transmits the block to all of the rest of the network. They verify it, and if it's correct, then they put it on the blockchain as the last block. Now we are more or less in 700. We're by the block 723,000, and it's been working like this since 2009 for 12 or 13 years. The other component of Bitcoin is that it has a fixed monetary policy. Each time there's someone that's making a lot of noise. Can you all guys mute your microphones, please?
Well, I'm listening to a blockchain course right now. So
I don't know if somebody can mute this person.
He is muted.
Yeah.
Let me check again.
But somehow we're getting all the noise from that mic. Okay. So basically, the fixed monetary policy consists in Bitcoin, in the case of Bitcoin, since the first blocks, the first 4 years, which are 210,000 blocks, 50 Bitcoins were paid per block to the miners who found the block. Then in the next 4 years, it was 25, then 12 and a half. Today we are in the fourth era, so it's 6.25. In the next 4 years, it's 3.125, and so on, until it reaches 0. And the total number of Bitcoins that are going to be issued ever in the history of humanity is 21 million Bitcoins. So this is algorithmic. It's part of the protocol. It's in the software, and it's fixed, and that's why it's called fixed monetary policy. The benefits of proof of work, which is the second big part, the most important part of Bitcoin or proof of work blockchain, are 5, and this is very important to understand. First was the original thing that they were looking for, which is this digital gold thing. So the cost of creating blocks is equal to the cost of creating the currency. So just like gold, it's very costly to create. This is why gold is scarce, and this is why gold is valuable. So that's the first thing that proof of work does. It mimics the cost of creating gold in the real world. The second thing is that it enables consensus between the computers, and this is Jalen. This goes to answer your question. It enables consensus because when all the nodes receive a block, and they see that the work was done, they know that that is the correct block. And because they know that is the correct block, and they verified all the transactions and they all had balances, then they reach consensus and they put it as the last block. That's the only information they need to know which is the last block, and they put it on the blockchain. They don't need to communicate between themselves. They don't need to check anything else. They don't need to go to a website, or they don't need a manager to be telling them which is the good block and which is the bad block, or anything like that. Just by receiving a block that has the proof of work done, it's sufficient information for the 80,000 nodes around the world, even though they're in different countries, in different languages, in different cultures. Some, like in Ukraine, are at war, or Afghanistan, or some parts in Africa. Some are in very unstable economies like Venezuela or Argentina. It doesn't matter. They know that that is the correct block. Transactions are good, and they put it in the last in the chain as the last block. This is very important because this is what, and the only way to attack this is if you have the same or more computing power than all the miners in the network. And this is what increased the protection to double spends. The other thing that this information does, this focal point of the proof of work that creates this consensus, is that it creates a safe focal point for entry, exit, and re-entry of the network. This is also a key thing, a key security component, because it's actually what provides permissionlessness. We all talk about permissionlessness when this is the component and the feature of proof of work that creates this. Why? Because if you are a guy and you just downloaded the Bitcoin software and you just want to enter the network, you run the software and it starts communicating with the other nodes, and it starts receiving blocks, and you're gonna know that because the chain of proofs of work are done, and because they're cumulative, you know that the one that has the amount of work demanded by the protocol done is the correct one. So it's very easy to know which is the right chain. If you start receiving blocks from an attacker and you verify the proof of work and it didn't hit the target, so the work is less, then you know that those blocks are not the correct ones. So it's very easy to contrast by any new entrant which are the correct blocks and which are not the correct blocks. And it happens a lot that your internet can go out, or your power can go out, I don't know, in countries or in cities, etc. So your nodes are out, your machine is out of the network. To come back to the network, it's also very easy because of this focal point. And again, you don't have to consult with anybody. You don't have to check with a friend, or subjectively, there's nothing to do. You only check the objective information of the energy spent in proof of work, and that's the only information you need to know which is the correct chain and to enter again. Then the last two security points or security features of proof of work are very important. We know them more. The are the most well known, which is that to enter new transactions, new incoming transactions, the proof of work protects them, because you know that when you receive a block that did the proof of work and verify the transactions, you know that is the correct block. So those transactions are protected. Why? Because if there's an attacker sending an alternative block with fake transactions, but it has less work than the miners of Bitcoin, then you know that you have to discard that one and you put the correct one. So the current state or the incoming transactions are protected. But most importantly, because in the last 723,000 blocks, all the work of each block is accumulated. This also protects the history of transactions in Bitcoin or Ethereum 1 or Ethereum Classic. Why? Because when you enter a transaction now, we are in the block 723,000. It's a certain level of work that was done on that block. But if you entered the transaction a year ago, say 50,000 blocks ago, to be able to reorganize or to delete that old transaction that was done a year ago, miners would have to, or the attackers would have to redo all the 50,000 blocks with all the proof of work, again, spending all that electricity just to delete that transaction. So the older a transaction gets, the more secure it gets, because it's practically impossible to get so many computers to reverse the blockchain. Not only because it's not only about computing power, it's computing power plus the capital and the expenditure in electricity.
Donald,
Yeah.
I have a question.
Mhm.
All right, so I noticed how you said the longer the transaction stays in the blockchain, the more secure it gets.
Yes.
And I was thinking about, when you said that, I was thinking about confirmations. So I watched a video about confirmations, and I heard that the more confirmations you have, so let's say if you have 40,000 confirmations, that means the transaction goes back 40,000 blocks.
Yes.
So I was just relating
Yes.
that to what you said.
Exactly. Confirmation is basically, yes, another word for blocks. So when you say 10,000 confirmations, it's 10,000 blocks. So when you send money to Coinbase now, they ETC, for example, they wait 3,000 confirmations before crediting the ETC into your account inside Coinbase. Why do they wait?
Okay, and they would
Mhm.
and they would do that to make the transaction more secure.
Exactly.
Okay.
Because the more confirmations a transaction has, or the more blocks on top of that block, the more secure that transaction is. Also, because I'm going to talk about this later, sometimes there's short-term chain splits. Sometimes two blocks are the ones that everybody receives, and they don't know which is the correct block. So they have to wait for the next block to know which is the correct chain. So those are like short-term reorganizations that are normal in proof of work. So they also wait 2 or 3. And in the case of Bitcoin, they have to wait 2 or 3 blocks to know if that block is the correct one. So that's another reason. But the main reason is because the older a transaction is, the more difficult it is to reverse. So that's why exchanges use many confirmations, no? For depending on the network. I think for Ethereum they use 50, for Ethereum Classic 3,000, for Bitcoin they use 3 to 6. It's all personal policies of the net exchanges. It's important to know about this thing about confirmations, that when you send the transaction to Bitcoin and it's accepted and it gets into a block, that's it. The transaction is already in the network. The thing is that, so in the case of ETC, in 15 seconds, usually your transaction is inside the network. The thing is that the choice of waiting many confirmations or many blocks to release the money, or to be sure that the money is received, is really a personal policy of the receivers that we should all have. When somebody sends us a Bitcoin, we shouldn't give them whatever they bought from us immediately. We should wait at least 2 confirmations. And the same thing with ETC. We should wait, I don't know. Now it has MES, so it's much more difficult to attack. I would wait, let's say, 50, 100 confirmations before doing that. But the security in terms of confirmation is the receiver's responsibility. Okay, back to Bitcoin. So all these benefits of proof of work are the key of the invention of Satoshi Nakamoto, and all this mechanism is called Nakamoto consensus, because it has full transmission, full replication, proof of work, block production, and a fixed supply, no, the payments to miners. And what does Bitcoin accomplish? Trust minimization, which means decentralization, which means security. No, these 3 things in the case of the blockchain industry are synonyms. Trust minimization, decentralization, security are synonyms in the industry, in my opinion. Then Bitcoin survives a nuclear war because there's full replication and there's nodes now in the North Pole, in the Southern Pole, in China, even if it's prohibited, and even though there's war in North America, South America, Africa, everywhere, even in space, it's so replicated that it doesn't matter if big chunks of the network goes down in a nuclear war, because there's always going to be a node somewhere running, digamos, processing transactions and blocks. So this is the key. When we say the phrase survives a nuclear war, it's that kind of metaphor. And lastly, it's hard money. Finally, the goal of hard money of Cypherpunks was accomplished with Bitcoin. Any questions? Any more questions about Bitcoin and this story and how proof of work works?
Maybe you can tell us about UTXO and how transactions are made.
That's a very good question. I actually deleted it from here because when I do this course with companies and multinationals and people who are noobs, it's too much information, too complex. But yes, so transactions, Bitcoin, it's a ledger with accounts and balances, and it accepts new transactions. Bitcoin uses what is called triple entry accounting, which is basically that in the transaction you have all the information you need, which is the original account, the receiving account, and how much, and that information is stored as it is in the blockchain. This means that if you have account A and move one Bitcoin to account B, and then move that Bitcoin from account B to account C, the way for the network or a node to check whether account C has one Bitcoin is to check to the past every single transaction. So they have to check first that the money was moved from A to B and then from B to C. So you have to check all the chain of transactions all the way to the past to be able to know which is the balance of the account at the end of the chain. Each one of these transactions, when they reach the end of the chain, where they point, say, one Bitcoin to an account, to account C, that last transaction is called unspent transaction output. The first one from A to B is a spent transaction output. Why? Because there was another transaction on top of it that moved it from B to C. So the chain of transactions, all the chain, they're all spent transaction outputs. And the last one is called unspent transaction output because it hasn't been spent yet. So the owner of that balance is the last account in the chain. So it's a little bit complex the way it works, and I don't know why Satoshi Nakamoto did it like that instead of using just the regular system, which is what Ethereum uses. So that's how the transactions and accounts on the UTXO model works. Did I answer correctly, bro? Was it clear?
It was for me. Thank you.
Another thing to understand is that here, public key cryptography, so this is basically our private key when we use a blockchain, and this is the public key. In the case of Bitcoin, the public key, which this is the one that I put here, it's transformed into a different format. It's the same number. This is hexadecimal, but it's transformed to base 58, a special base 58 of Bitcoin, and the accounts in Bitcoin really look like this. So your public key, even though it's this number, it looks really like this inside Bitcoin. Any more questions about Bitcoin? Okay, I'm going to Ethereum. So Ethereum came after Bitcoin in 2013. It was created by Vitalik Buterin. Vitalik Buterin is a young computer scientist. He's not a cypherpunk. He must be like 28, 29 now. And when he was in his early 20s, he had the ideas to put together a blockchain just like Bitcoin with proof of work, accounts, balances, etc., but that it could support smart contracts, which was the other goal of Cypherpunks, so that it would become programmable. No, so it's the same as Bitcoin, but adds programmability. In the case of Ethereum, it doesn't have a fixed monetary policy, even though it's algorithmic. They have changed it several times, so this gives us the information that it doesn't have a fixed monetary policy. And the Ethereum network not only has accounts and balances, but also stores software programs. So you write a software program, you send it to the network of Ethereum. It has more or less 6,000 computers around the world. And when it hits the network, it gets transmitted everywhere in the network, and it gets replicated everywhere in the network. So when you send it, it becomes a decentralized software program. So that's what a smart contract is. It's just a decentralized software program. That's it. It gets replicated in all the nodes of the network. The components of Ethereum, the brilliant invention by Vitalik was to put all these 5 things together. First, he created the virtual machine, which is basically a piece of software that is replicated in all the nodes of the network, that understands a series of opcodes, of operation codes, which is how computers work, and it's replicated everywhere. So that this is what gives the nodes the ability to receive these programs and be able to compute them. That component, the virtual machine, is called Ethereum Virtual Machine, or EVM. Ethereum Classic is also an EVM chain, fully compatible. Then he invented a programming language because he got JavaScript, or a member of his team got JavaScript, and he modified a little bit so it could work in a decentralized network. So now it's called Solidity. So I think that, I'm not a programmer, but I think that programmers who know Java, it's pretty easy for them to understand Solidity. And Solidity is the only program for now that the Ethereum network understands. So the software programs are written in this language. The other thing is state transition. So this is related to what I explained of the UTXO model in Bitcoin. State transition means that, unlike Bitcoin, that you need to check all the history to the past to know the balance of an account, state transition basically means that you have an account and a balance, you receive a new account, or in the case of the whole network, you receive a new block of transactions, a new transaction or a new block of transactions, and the whole state of the network goes through a transition from state A to state B with that new information. And you can forget the past. So there's no need, when you check an account balance in Ethereum, you just go and the network gives you the information, account, balance, that's it. In Bitcoin, you have to check all the chain of transactions. In Ethereum, no, it's just a final state. It has a state, receives transactions, and it migrates the state to a new state, which is called state transition. That model is much more easier for machines to handle, to make regular computations. That's how computers work. And so the combination of the virtual machine plus the programming language plus state transition is what enable programmability in Ethereum. But then there's a problem that is not solvable in computer science, that sometimes programs they just start doing cycles and they can never end the execution. No, it's called the halting problem. So when we have a Windows computer and you run you're using an app, and suddenly the clock starts to go around and it never stops, and you have to turn off the computer and turn it on again. Well, that's the halting problem. There was some problem that the execution didn't go right, or the software program may have a bug, that it doesn't let it halt or finish the execution. So Vitalik invented the gas system for this, because if you have a computer, you just turn it off and on, or you turn off the application and turn it on again. If you have a network of 6,000 computers that is supposed to be trust minimized, you would have to call everybody whenever a program gets, goes into this endless cycle. You would have to call everybody, and it would be centralized. No, this is how Solana works. It has halted. They had problems several times, and they have to call everybody and tell everybody to turn off their computers and turn them all again on again. In the case of Ethereum, you cannot do that. So the invention by Vitalik was this. Okay, let's do this. When you send a transaction, that transaction may go through and execute normally, or it can have the halting problem. So let's do this. Let's put an arbitrary number, an arbitrary unit called gas, and we put a gas limit. And when all the computers in the network get reach this gas limit, when they're processing that transaction, if they didn't reach a conclusion or an execution, a full execution of that transaction, they just return the transaction as that they couldn't finish it. No, and to know that they had to finish is because they used up all the gas in that transaction. It's more or less like you have a car and you put only 1 gallon of gas, and you go in a highway, and after 30 or 35 miles, 40 miles, the car is going to stop automatically. Why? Because it ran out of gas. One of the same thing with the gas system. Each transaction has a gas limit, and the network knows that they have to execute the transaction. If it executes correctly, then no problem. They get the money of the gas fee, the payment, and everybody's happy. If they reach the gas limit and they couldn't execute the transaction, they return the gas to the sender, and they tell him that they couldn't finish the transaction. They couldn't execute. So that was another key invention by Vitalik, which is brilliant, that enabled programmability in a decentralized network. And finally, it stores the programs inside the ledger. So it has accounts, balances, and the space to store decentralized programs. What this enables is applications, that what we know as apps, that when you send them to Ethereum, they become decentralized applications. So we call them dApps. And finally, one key thing about Ethereum is that it's actually moving away from proof of work and is going to proof of stake. An account in Ethereum is here. So this is the same account is in here that in Bitcoin would look like this. In the case of Ethereum, it looks the same way. They just add OX, which is something that is common in cryptography. So the accounts in Ethereum look like this, and Ethereum Classic as well. Any questions about Ethereum or how the EVM system works, or the invention by Vitalik Buterin?
I have a question about Solidity.
Mm-hmm.
So basically, you write the code there, right? And then you compile it to bytecode and send it to the blockchain. Is there a limit on how much code you can have?
I do not know that. I believe there is a limit. I think that there is a X amount of size a program can have. And I think that change was done after Ethereum was created. And I think we imported this in Ethereum Classic as well. But unfortunately, that's something I don't know for sure.
Okay, no problem.
I think there is.
Hey, I saw. Can you guys hear me?
Yes.
I saw a video where they were talking about blockchain and information, and they said usually it's good to have less data because uploading data on the blockchain is really expensive.
Yeah. Yeah, so I think that that must be one of the ways of limiting the size of contracts, no? That the bigger the smart contract, the more expensive it is to send to the network. But that's a good question. I'm going to write it down because I need to be able to answer it when I present this. Limit. Very good. Any other questions about Ethereum and how it works? Okay, now I'm going to explain the differences between proof of work and proof of stake. Now that I have explained the history, from HashCash to BitGold to B-Money, how Bitcoin works, the features, the 5 features of proof of work that make it work in a totally decentralized way. I'm going to explain the contrast between proof of work and proof of stake. Proof of stake is a technology that came years after proof of work. Basically, the criticism of proof of work is that it uses energy, and that is bad for the environment, which is false. And I'm going to explain why it's false later. But there were concerns about the environment and also concerns about scalability. Nakamoto consensus, because it uses proof of work, blocks, full replication mainly, and full transmission of the information, then the blocks need to be limited in size so that the information is easily distributed around the world in seconds or milliseconds. And even if bandwidth is low or local processing power of the computers everywhere in the world, even if it's high or low, the blocks can be processed, so they have a limit. And this is why Bitcoin can only process up to 4,000 transactions per block, which is 576,000 transactions per day. However, Visa processes billions of transactions per day. And the same goes with cloud services and Google and all the payment systems and the banking system. So that's the main, I would say, legitimate criticism of proof of work and Bitcoin and Ethereum Classic and Ethereum 1, which is that they're not scalable. So basically, proof of work uses energy, but proof of stake uses deposits of money. So what they did is, okay, let's get rid of the miners that create the blocks using proof of work, and let's replace them with people who put deposits of capital. They put money in an account inside the network, in a special account, and just because they put money, the assumption is that they're going to produce the blocks and they are going to be honest. So basically, instead of being miners that produce blocks based on work and creating this hash function or this hash cryptographic stamp, it's people that put deposits, and because they have that deposit, then they earn the right of creating blocks and hence earning the reward per block. And they become the stakers in the network. And we all have to accept their blocks. So that's the difference between proof of work and proof of stake. The thing is that proof of work is much more secure than proof of stake because it has the 5 features that I explained before. And proof of stake basically throws away all the features. It has no way of knowing which is the correct chain. So you have to check with block explorers or friends or somebody that you trust, which is the right blockchain. You have to trust that the guy that sends the block, just because they put a deposit, they're going to be honest. There's no focal point for entry, exit, and entry again. So if you get kicked out of a network because your power runs out, you have to check again with a friend or someone, a block explorer or a website in the internet, which is the right chain. And there's no work protecting the network. It's just the fact that some guy put money, and that's why I have to trust this guy. So there's no computing power protecting the network. It doesn't create a barrier for sending fake blocks. And not only that, if the stakers get together, they can redo the blockchain in seconds. In Bitcoin or Ethereum Classic or Ethereum 1, if all the computing power of the miners, they collude and they want to reverse the chain for a year or 2 years, they have to go through an enormous cost in energy and computing power to be able to do it. In proof of stake, they just do it in seconds. Why? Because there's no work done on a block that is accumulated on a block by block basis. However, in terms of security, the reason why proof of work is more secure also is because it's much more simple, and proof of stake, because it needs all these complex, weird rules to slash the guys if they send dishonest blocks, etc. It's very complex. They have to add a lot of complexity to create the impression that it's more secure. But the truth is that if 1/3 of the nodes colludes, they can mess up the network anyway. So they go back to the normal Byzantine fault tolerance before proof of work. And this is one example of this issue of complexity. Lynn Alden, you can Google this. She wrote an article a few days ago about proof of stake complexity, and she has this citation there where she cites Ben Eddington, which is a developer of Ethereum that is working on the proof of stake clients, and he said you can code up a proof of work algorithm in 100 lines of code. Our current clients, which are proof of stake, are 100,000 lines or so for proof of stake. 100,000 lines. Imagine all the complexity and all the bugs and all the problems that can be there hidden that we don't know. So that's another reason why proof of stake must be more complex, more insecure. So the end result of this, which is very important for the industry because they're actually complementary, is that proof of work is more secure but less scalable, and proof of stake is less secure but more scalable. So I'm gonna explain this in the second part of the course on Wednesday. Both together very likely are gonna work in tandem to provide the whole service of the blockchain and the whole promise, which is secure and scalable. Then there is another third clown kind of consensus mechanism, which is proof of authority, that Ripple uses this, and all the chains that are like Ripple, and I think that BNB also uses this proof of authority, which is basically they select a group of trusted node operators, and they say, okay, because you have a great name and you are trusted in the community, you can make blocks, and we're going to pay you for each block. So this is a clown show, and it goes back towards what we are trying to avoid now, which is the trust that we are depositing in banks and corporations and governments to run our platforms and systems. No, so this is the third kind of consensus mechanism. Any questions about proof of work versus proof of stake? One thing that is very likely going to happen to proof of stake blockchains, if they stay pure and do not anchor their states and monetary policies to proof of work blockchains, is that the stakers, even though you can start with a new proof of stake blockchain with 100 stakers and you think, oh, this is decentralized, in the long term, just because of normal economies of scale and power law, a few of those stakers, just because of their competition, are going to get bigger, and the majority are going to get smaller. And I believe that in the future, only 3 or 4 big stakers are going to be the big stakers in the proof of stake networks, and they're going to be 3 or 4 big banks. And then you're gonna have from the 5th to the rest are going to be, digamos, irrelevant or trivial, insignificant players in that blockchain. And those 3 or 4 likely are going to have 80% of the market share of staking. We already see that today. Coinbase is providing staking services. Binance provides staking services. They have millions of they have hundreds of thousands of Ether and Cardano, or millions of Cardano, and millions of Solana, and people go and send them. So they become these big institutions that are going to be the big stakers. And once they have that power, they can just make the changes they want. So if they get slashed, for example, because there was a computer glitch or a bug in the network, they're going to just reverse the network and get their money back. So the security model is very weak in proof of stake. It's completely subjective. And in proof of work, it's completely, I would say not completely, but 99% objective. I'm going to explain why it's not 100%. If nobody has a question between the consensus mechanisms, then I'm going to explain how proof of work works. I wrote this, but okay, this is a slide of how proof of work works. This is, we're reaching the end of today's course. How proof of work works. When basically the miner gets the previous hash of the previous block. This is why it's a chain of blocks, because each block has the hash of the previous block. So it creates a chain, and it's called blockchain. The second piece of data that they get is the hash of the current transactions. So they get 4,000 transactions. In the case of Bitcoin, they make a hash. It's not proof of work. It's just a trivial hash. And they get that hash, and they add it to the data that they have to process. They get the timestamp. They put the Unix time into the information, and they add an arbitrary number, no, an iterating nonce. Once they get this, they hash that information, and they're going to produce a hash, which is a very big number. And if that hash doesn't hit the target provided by the blockchain, by the protocol, and it hits here, for example, then they have to throw it away and start again changing this number. And they repeat that millions of times per second or trillions of times per second, and the great majority hits outside the target. That's why they have to repeat. They get the block of transactions and they hash it, throw it away, hash it, and they repeat it millions of times or trillions of times per second. And the great majority are not going to hit the target imposed by the protocol. This is why they have to work so much and burn so much energy, because they have to repeat this process so many millions of times per second. Until one of the miners, randomly, this is probabilistic, finally hits the target. And when he hits the target, he gets that stamp, puts it with a block, and sends it immediately to the rest of the network for verification. And the rest of the network has to verify it. And if it's actually correct, indeed correct, we're going to say, great, we're going to get your account and credit you with 6.25 Bitcoins, which is the current payment, or in the case of Ethereum Classic, 3.2 ETC. So this is how proof of work works, and this is why they burn so much energy. And this is what has all those benefits that I mentioned before. In the case of proof of stake, they just get the information, they form the block, they send it, and it has to be accepted. There's no work done. In the case of proof of stake, they pay when they have many stakers. They just choose one to get the reward with a lottery system. In the case of proof of work, it's because they actually did the work, and that's why they got paid. That's another thing of proof of stake. It has no cost to participate, other than making a deposit, which is a passive kind of thing to do. In the case of proof of work, you have to invest in machines, you have to buy electricity, you have to move to another country, the electricity is less expensive somewhere else, or you have to move to another country, another place if it gets prohibited. It's a lot of work and risk to be a proof of work miner, and that's why the payment to them is called fair. No, the distribution of money in those systems is called fair. In the case of proof of stake, just because you have a lot of money, like a bank, you put it there and you start getting money. Okay, so anybody has questions about proof of work and these comparisons and how it works, etc.?
I have a general question. do you think that proof of stake is more inclined to hybrid with current systems, with current bank system, financial systems, and I don't know, maybe join together and offer solutions for customers in a hybrid way, combining the two systems?
Yes, I think that this is going to be on Wednesday in the second class, where I'm going to talk about the layers, components, etc., and exactly these things. I think that regulated financial institutions in the world are going to be the stakers in the proof of stake blockchain. They're going to take over because they just have more capital, and any individual, unless you're a super trillionaire or billionaire, you cannot compete with a bank. And I think that the closed platforms of the banks are going to migrate to proof of stake, and channels and rollups and all these new technologies that are very scalable. And they are going to be the stakers in the winning blockchains. I think there's going to be in the proof of stake layer, I think there's going to be 3 or 4 winners, like Ethereum 2, BNB, Polkadot, Solana, something like that. And then the rest are going to be smaller and very insignificant. And the big stakers in those networks are going to be the same banks: HSBC, JP Morgan, the Bank of China, stuff like that. Maybe even the central banks, Citibank, etc. And they are going to offer all these DeFi products, lending, deposits, if you think about it, the financial products are the same. A deposit is a deposit in a centralized system or in a decentralized system. It's basically I send the money and I get interest. And the same thing with a loan, no? I get a loan and I pay interest. It doesn't matter if I get it from a decentralized or decentralized. So the core products are the same. The same with insurance. The core product is the same, or mutual fund or asset management. All those things are essentially, or exchange services. You just match a buyer and a seller. But you can do it in a centralized system like it is today, that they're all run in cloud services. Sometimes the banks tend to have private cloud services, their own infrastructure, but some of it they delegate to AWS and IBM Cloud and stuff like that. Or you can migrate all that to Ethereum 2, BNB, and all these decentralized proof of stake networks, or seemingly decentralized proof of stake networks. I think that's going to happen. I think in the future, all of our financial products and accounts are going to be on proof of stake blockchain. So you could call that hybrid, or just the fact that the financial industry migrates all the way to proof of stake. That's my vision. Did I answer the question?
Yes, thank you. Very clear.
Okay, so a little bit of history of Ethereum Classic. So Ethereum Classic is the original chain. It was created in 2015, but the split between Ethereum and Ethereum Classic occurred in 2016. What happened is that there was a dApp called the DAO that was basically a mutual fund where everybody could send money, and it accumulated $150 million of money. And all the people who sent money would get the token of that dApp, and they could vote on how to invest that money. So that everybody was very happy, everything. And one day, it had a bug, and a hacker stole $50 million from that dApp. It was 3.6 million Ether, 3.7 million Ether. And it created a crisis in the community because we were a very small community. Ethereum was worth very little at the time, and everybody was stressed because it could mean the end of Ethereum, or this big owner of Ether could theoretically also control the network. So there was a lot of debate on what to do. There was a big majority of the network that decided to violate the principles of a blockchain and do a manual intervention and do an irregular state change on block 1,920,000, which was in June, July of 2016. And there was a minority of the blockchain, the ones who preserved Ethereum Classic, the original chain, which must have been less than 5% of the network, who said, no, we have to preserve the principles of a blockchain, and we are not going to do an irregular state change and return the money to the owners, to the original owners, and the hacker is going to stay there. And if anybody wants to solve that problem, they have to go through the courts, the FBI, Interpol, whatever, but you cannot change the state of the network. So that's what divided Ethereum. We were all one community and one network in block 1,920,000. The heroes of Ethereum Classic decided to stay with Ethereum Classic, and it's now the original chain, and this is Ethereum Classic. And the big community and the Ethereum Foundation and the leader Vitalik, etc., they decided to fork. So this is a fork. Ethereum is a fork of the original chain. Ethereum will move to proof of stake, as I said before, and has no fixed monetary policy. That's a big difference between Ethereum and Ethereum Classic. Ethereum Classic will stay with proof of work and a fixed monetary policy. And you could say that Ethereum Classic, because it has the base of Bitcoin, but it has smart contract, is the technology of Ethereum with the philosophy of Bitcoin, because we have the same principles. When this event happened, this is where the code is law motto was created, no? Because the community that stayed with Ethereum Classic wrote the Ethereum Classic Declaration of Independence, amongst other documents, and that document has this phrase that says, "Code is law. There shall be no changes to the Ethereum Classic code that violate the properties of immutability, fungibility, or sanctity of the ledger. Transactions or ledger history cannot for any reason be reversed or modified," which is exactly what Ethereum did. And this is the origin of the motto, "Code is law." Finally, I just want to clarify something. This is the end of part 1 of the course. The proof of work security model has a physical layer and a social layer. So this is why it's not 100% bulletproof. This is very important to understand. The physical layer, which is the operating network of Bitcoin, Ethereum 1, Ethereum Classic, etc., is protected by cryptography, and it has this consensus mechanism based on proof of work. But if somebody has 51% of the computing power of the network, then they can do an attack. It's not really a hack. It's just an attack in the sense that they can do a double spend. You can Google what is a double spend. Basically, it's to steal money on the blockchain. So there is a known attack vector and risk in proof of work blockchains. Everybody knows this, and this is good because this is the transparency of the blockchain industry. We're going to talk about transparency on Wednesday in the second part. But the social layer still has some power over the physical layer. So it is possible, for example, for all the 80,000 nodes and developers and miners of Bitcoin to get together and for some reason, crazy reason, say, let's increase the supply and let's go back to 50 per block, and they violate the $21 million fixed supply, for example. That would be a social attack. And it is possible. It's extremely unlikely because it's a coordination problem, but it is possible. So many people ask or have these myths that Bitcoin and Ethereum 1, Ethereum Classic, and all the proof of work, Litecoin and Dogecoin and all the proof of work blockchains are trustless. That's not true. They're trust minimized. The correct term is trust minimization, because there's a small sliver of risk that these networks still have. In fact, ETC has been attacked with 51% attacks. Other blockchains have been attacked. I'm sure that, and successfully attacked. No, I'm sure that Bitcoin, Ethereum 1 were also attacked, but they were not successful because they have bigger mining bases, more computers mining. but this is important to clarify. It is very important to, in the social layer, it is very easy to make a change that is not controversial. For example, an upgrade to ETC, an upgrade to Ethereum 1, or an upgrade to Bitcoin. For example, the last upgrade was in Taproot in Bitcoin. If everybody thinks that is good and it really makes the network better, it's very easy to do those changes. But whenever there's controversy or something is not popular, like for example, if somebody proposes to change the monetary policy of ETC or Bitcoin, then it would be extremely difficult to pass that and to actually for it to reach the physical layer and to change the rules of the physical layer. So it's very important to understand these things. It is a matter of being rational and understanding the probabilities of these things, and to understand that these risks exist, but it doesn't mean that they're insecure. They're systems that are highly secure just by the sheer reason that they are decentralized. And that's it. Next time is going to be the second part of the course, which is categorization and use cases of blockchains. Does anybody have any questions about this part? Any questions about the first part of the course? Very good. Okay, I assume there's no more questions, so I'm going to end the call. Thank you very much, everybody, for participating.